Here's a similarity between TCP and UDP that ties into what we were talking earlier about your classes of traffic. And here when 10.11.11 sends packets to 10.11.100, it's all sunshine and lollipops if there's only one type of traffic being transmitted. How often does that really happen though? What if we have multiple types? Because that host could be sending file transfer via TFTP, could be sending some email via SMTP, and some website data via HTTP. Well, in that case, we got three different flows of traffic going from one host to the server, and the server's got to have a way to keep those incoming flows separate so it can send each type of data to the appropriate application. That's where well-known port numbers come in, including three that I know you bumped into during your CCNA studies. The TFTP flow being on UDP port 69, SMTP flow TCP port 25, and HTTP flow TCP port 80. Stepping away from this for just a moment, speaking off the record as I am talking into a microphone right now, remember when you were memorizing all those port numbers just as you're starting, you're thinking, do I really have to know this stuff? And it really does come in handy later, not just for certification exams. It does become second nature after a while. But that's one of the first things you have to memorize, just like, oh, please let me just remember all these numbers. Well, these well-known port numbers, though, they allow that recipient to know how to handle the incoming traffic flows. When a host receives data marked with UDP port 69, it knows the traffic needs to go to the TFTP application and so forth. These port numbers also allow the host to mix the data types during transmission rather than sending all the TFTP data first, then the SMTP data, then the HTTP data, etc. This mixing of data streams is referred to as multiplexing, and it is supported, as we can see, by both UDP and TCP. Now let's take a look at some TCP features that you likely did not see during your CCNA studies. We know that the TCP sequence and ACK numbers can be used to detect lost segments. And we love that about TCP, but the process is not always as efficient as we would like. Because while the lost segments are detected and retransmitted, we do end up with some segments being retransmitted when it's really not necessary. Now, TCP selective acknowledgments make that overall process a lot more efficient since the client can indicate exactly which segments it did receive. Now, without selective ACKs, we end up with something like this. Let me bring the diagram up. And we all go through something like this when we're first learning networking. We see that 4 segments are going from one device to another, and for some reason segment 2 doesn't go through. So our laptop friend there, or whoever the client happens to be, would send an acknowledgement back and just saying, hey, I'm acknowledging 1. And then the sender would end up resending what? It would end up resending 2, 3, and 4. Well, again, the job gets done. The lost segment gets handled, but it's not as efficient as we would like because segments 3 and 4 are being resent, and the recipient received those, but the original form of TCP, or the original acknowledgement, cumulative acknowledgements as it's known, that doesn't really give the recipient the chance to say, I'm acknowledging this one, but I also got these. But TCP selective acknowledgements does make that happen, because here, TCP, the recipient, with TCP selective acknowledgements, the recipient is ACKing 1 and sacking, as we call it, selectively acknowledging 3 and 4. Basically, that recipient is saying, I'm acknowledging 1 and I got these others, but they don't follow the numeric pattern. So it looks like we lost something there. Well, the sender sees that and says, oh, okay, I just need to resend 1 segment. I need to resend segment 2, and that's exactly what happens here. Pretty cool stuff. Now, to enable this on a Cisco router, we're going to run IPTCP selective ACK in global config mode. And I've brought up here for you on the live equipment. Let me adjust that just a little bit. And this is a picture of all the IPTCP options. We're not going to look at all of them, but I do want to show you a few. And selective ACK is the one we're looking at right now. And of course, you know what you're always holding your breath about. It's like, okay, what options do we have? It's good to have options, but sometimes we get too many, it seems. And here, frankly, you don't get any. So you're either sacking or you're not. It's an all or nothing deal, but that's what selective acknowledgments do for us. Now, about those timestamps, and let me bring that back up and you can see timestamp, and iOS help tells us that that enables the TCP timestamp option, and that's very helpful to know. But from forensicswiki.org, TCP timestamps are used to provide protection against wrapped sequence numbers. That's great, but here's what I'm really looking at. It is possible to calculate system uptime and boot time by analyzing TCP timestamps. These calculated uptimes and boot times can help in detecting hidden network-enabled operation systems, linking spoofed IP and MAC addresses together, etc. Okay, well, that sounds great, but there are some concerns with TCP timestamps and security vulnerabilities. I would do research beyond the scope of this exam before I ever use them on my network. You know, it's one, you know how it is. You go out on the internet, it's like, you know, one guy will say, oh, this is the greatest feature ever, and another one will say, oh my gosh, I can't believe you're running that because it makes Martians, puts Martians in your network, you know, that kind of thing. But do your own research on that before you enable it. Now, on Cisco routers, just use IP TCP timestamp, and I believe this is another one with no options. Let's have a quick look. Yep, no options there either. Well, 2 for 2. All right, one thing I do note here, because TCP header compression is so popular, I did want to tell you or note that TCP header compression does not work when TCP timestamps are enabled. So that's a good thing to know. Now, this Keep Alive feature, I get asked a lot about this one. I know I'm referring to the NA course a lot here. Excuse me, there, copy over. I get asked a lot about this one in my CCNA course, usually after I've hit them with one L2 Keep Alive after another. You know, we got this clock rate we got to have for point-to-point connections, and we got to have frame relay LMI, we got to have this, we got to have that. And what's the one service that we learn about in the NA studies? Because a lot of these you could go a long time and not even know what they are, but especially not use them. The one is service password encryption. So when I bring this up, I always like to bring up the the material on the live routers, and someone will see the TCP Keep Alive's in and send me an email or a tweet and just say, you know, do I need that for TCP to work? Is that some kind of Keep Alive? Well, you don't need it to work to make TCP work. And as you can see, what it does, it generates Keep Alives on idle incoming network connections and Keep Alives on idle outgoing network connections. And the reasons to use these, in my humble opinion, are really few and far between. Now, these are disabled by default. They're not necessary for normal TCP operation. A search on Cisco TCP Keep Alive, the first thing it usually brings up is a document on how to use this feature to prevent hung telnet sessions. And that's outside the scope of the route exam, but I do have a link here for you might want to check out. A lot of people consider these Keep Alives to be security risks. I believe some Cisco security appliances, you learn some things you learn about in the CCNA security when they do a lockdown. This is one of the things that it'll actually turn off on the Cisco router is protection. I've worked with them in lab environments. I don't use them in the field. It's good to know they're available, but unless you have some crying specific need for them, frankly, I would leave them off. A quick word here about TCP ECN, or TCP Explicit Congestion Notification. And frankly, the name is the recipe. Enabling TCP ECN allows a router to notify hosts at the endpoints of a communication that there's congestion afoot. And that lets us know and gives us some support for traffic that is particularly delay sensitive. And we know what that means, voice and video. Again, we're going to run IP TCP and then just ECN if we want to enable explicit congestion notification. There are no options with this command either. So that's going to wrap up our look at TCP for right now. What's coming up next, we're going to do a quick and important review of PPP over a point-to-point link between a couple of routers in the lab. And then we'll talk for a moment or two about something called PPPoE, and that's coming up next.